Hi everyone! Matrices are a really useful topic in mathematics, with their use varying from linear transformations to statistics, probability, and beyond. In motion physics, the idea of rate of change can be seen in a lot of places, like we've seen last time. So what happens when these two ideas meet? Before we start, this is going to involve 2D motion, which requires vectors to convey. From now on, we're going to describe the position vector r of t as x of t, y of t. To take the derivative, we simply differentiate each component. So we get v of t equals dr over dt equals dx over dt dy over dt. We're also going to use the power series of e to the x later on. What if the velocity is a linear transformation of the position vector? Suppose that there's a 2x2 matrix M, A, B, C, K, such that when M is applied to the position, it gives you the velocity. We can write this as x prime of t, y prime of t equals the matrix A, B, C, K acting on the position vector x of t, y of t. We can use properties of matrix multiplication and expand this like so. We get x of t equals ax plus by, and y prime of t equals cx plus ky. Here comes the part that I find really interesting. Divide the two equations and you'll notice that this becomes an implicit derivative problem. dy over dx equals cx plus ky over ax plus by. Now, I confess, I haven't actually found a general solution for x of t and y of t. But what I can do is show you the case where one of the diagonals are both 0. When a and k are both 0, we get dy over dx equals cx over by. By moving the x terms to one side, the y terms to the other side, and integrating both sides, we end up with c over 2x squared equals b over 2y squared plus mu, where mu is a constant. Simplifying the equation, we end up with c over 2 mu x squared minus b over 2 mu y squared equals 1. What's really intriguing is that the graph of this is just a conic section. Assuming that mu is positive, if b and c are positive, it's a hyperbola. If c is negative while b is positive, we get an ellipse. How cool is that? If we want to parameterize this equation, we'll have to bring in the hyperbolic functions. Specifically, x equals the square root of 2 mu over c times cos of t, y equals the square root of 2 mu over b times sinh of t, where sinh and cos are the hyperbolic sine and cosine functions. The other way we can solve this matrix question is to compact x of t, y of t into the position vector r of t, rewriting it like dr over dt equals a times r, where a is the matrix A, B, C, K, of course. Then we're going to treat r of t like a number and move it to the left, move the dt to the right, and we get dr over r equals a dt. Integrate both sides, the antiderivative of 1 over r is natural log of r, and so we end up with natural log of r from r0 to r equals natural log of r minus natural log of r naught equals at. Using the log property that natural log of a minus natural log of b equals natural log of a over b, we get that the natural log of r over r naught equals at. Exponentiate both sides, and we get that r of t is e to the at times r naught. Recall the power series of e to the x. When we plug in a matrix, the 1 turns into the identity. So e to the at expands like so. Here, I'm going to show you guys another case where when a and k are both equal to 1 and c is equal to 0. Therefore, A is going to be the matrix 1b01, also known as a shear matrix. Using the property that this matrix to the nth power equals 1nb01, we get that r of t can expand like the following. Notice that the first and fourth entry both evaluate to e to the t, while the third entry is still 0. As for the second entry, write n over n factorial as 1 over n minus 1 factorial and separate t to the n into t to the n minus 1 times t, then pull the b times t out. Then, notice when n equals 0, we get t to the negative 1 over negative 1 factorial. When x approaches negative 1, the function x factorial goes to infinity. And so the first term goes to 0, so we can ignore it. So this series evaluates to b times t e to the t. Finally, multiply in the x naught, y naught, and we have our solution. The graph to the solution isn't as clean as the first case, but it is a decent solution nevertheless. Remember that in the first case, where a and k are both 0, we had an ellipse or a circle as the graph. Well, shapes like these are referred to as the conic sections, and they're the paths that a satellite makes around a planet. If b equals negative c, then the velocity would always be perpendicular to the position vector. In physics, this type of motion is called uniform circular motion, and I've talked about it in my last episode. As you can see, matrices are a really wonderful subject. Next time you come across matrices, think about how useful they can be, and it might motivate you to learn more about them. That's it for this episode. I'll see you guys next time.